So that's why these things won't work with small fuels. To make the small fuel, your targets, your combustion and cracking time is too short. You aren't keeping the tars in an open void space in there where they can do this cracking, and you don't succeed in finishing the reactions or finishing the cracking, and it comes out the end of the system. So, surprisingly, that's the fifth process, and by the mass balance, you're doing more cracking in here to generate CO2 and hydrogen than you are getting the CO and hydrogen from reduction. Okay? To make matters more complicated, you're also getting some CO and hydrogen from up here in pyrolysis. So, the usual explanation of the CO and hydrogen coming from reduction is a partial explanation. Questions?
So what is the ideal fuel size for?
In a traditional, well, it depends on the size of the reactor, but these sorts of sizes, in traditional Embert ones, they would run big chunks in like the 1 to 3 range, but those were made with special equipment. So one of the big things we were trying to do was to get them to work off of more typical chunk fuel, which our goal is to be able to make it work off of wood chips. Okay. So we've got it to work off of regular wood chip chunks, which are much more difficult than big fuel chunks. Okay. And we've done that through actually controlling the drying and pyrolysis processes, more so than dealing with this.
Have you run into a situation where your arc gets so hot that it melts down?
We've melted 2, but they really only melt down when you run them empty, and you no longer have the pyrolysis and drying happening above to be extracting temperature out of them. So the only things that we've had meaningfully melt down have been when people have run the thing dry too many times. Okay.
Converts are self-regulating. As the throughput increases of gas, as your gas increases, gas making increases, the charcoal increases. Actually, the temperature on the grate between the difference between the temperature at the restriction and on the grate nearly equalized as you would get. Well, it's just it uses more charcoal as your throughput increases. So it's pretty much regulating up to a point. The charcoal cools it down.
The combustion and reduction are self-regulating. To the degree to which you generate heat through combustion, you're going to get the reverse and equal amount of heat extraction into chemical energy through reduction. So this part of the gasifier is self-regulating. Okay? So you can take a pipe, put biomass in it, and you can run combustion and reduction down the pipe and get clean gas out the end.
Well, I think one of the challenges is, I think a lot of people like to run briquettes or pellets, but with the steam and sort of decomposes as it goes on. How can you harden that?
Well, you can put binders in it, or you can change the architecture of the reactor. You can change the way you run it. You can put airlocks in it. You can better separate the drying from the pyrolysis section. If you have just a straight vertical gasifier like this, you have tremendous difficulty with briquettes. But if you start breaking these sections up, so like on the GEC or the toddy, all this drying is over here on the side, and we're creating a progressive gas lock here such that it will, it's reasonably separated now for cleanliness. It's getting more so. If you want to get really fancy, you put an airlock in there, but an airlock costs, the airlock in that thing out there costs $9,000 or $10,000. They're expensive, and they're annoying. It's hard to get stuff to move through them. Okay, so you can be solved either by dealing with the fuel or changing some of the architecture of the reactor. Okay, so I got one more ring to go here, so we should not go too far, but go ahead.
Is there a ratio between the fuel size and the orifice diameter? Or is it just as long as it can go through it and be all right?
Well, in material handling, you usually say that you don't, an orifice has to be about 7 times the size of a solid piece of material that you're trying to pass through it. But that also varies depending on whether it's a cone or whether it's an auger boot with angled sides and straight ends. It varies on the friction on the wall. There's a whole bunch of different variables into that. But it's different here because usually this drawing is somewhat these nozzles should really be up here more at the top of the taper. And so the nozzles help blast the stuff through the smaller hole. Okay, so the reason on a downdraft gasifier you can in fact get these fairly large pieces of material to go through there is first they go through pyrolysis that makes them smaller. And second, the air blast pushes them through. Okay. So, I mean, on our 3-inch gasifier, we run stuff up to 1.5 inches. But if you just had a 3-inch hole and poured 1.5 inch fuel on the top, it would never go through. Okay? So, but by the time you have it there, you don't have your original fuel. You have something very different. Okay? So, that's the cracking process that's going on in a downdraft gasifier is very critical. And there's ways that you can start fixing this by creating purpose-made void spaces down in here where you do the cracking separate of the bed. If you separate your combustion of tar gases from the bed and create an environment where you keep those combusted gases out of the bed during the cracking time and then reintroduce them in the bed, you now don't have the dependency of that void space in the fuel. Okay? And we have some reactors that are coming later that do that. So then that starts to allow you to run more granular fuels. But no one does that. Okay? Okay, so that's the 5th process, and it's sad that the instruction materials typically don't include it. The problem with that explanation is it's also wrong, or rather it's incomplete in really significant ways. That explanation, the third ring explanation, suggests that there are these discrete processes called drying, pyrolysis, and combustion, and reduction, and cracking that are these one things that we line up and take arrows between boxes and whatnot, and it operates. In reality, each one of those processes is a highly variable thing that, depending on the conditions that it's happening under, the outputs of it can change radically. So not only are you trying to control these inputs and outputs, you're also having to deal with the conditions within each of those processes and optimize them such that the outputs that then get used at a later stage work with what you're trying to do. Okay? So a lot of what we're doing in the GEC is trying to capture and take control of each of those processes individually and control the parameters of that one process in the manner that optimizes the outputs and whatever is best for the system, which varies between these different processes. Okay?
I've often wondered how many times water would get dissociated and then gone back to water before it actually
goes back and forth. It can bounce back and forth a whole bunch of times.
Free oxygen actually hooks down to the crack. I mean, this probably does a whole bunch of that.
Yeah. Yeah, the kinetics of those reactions get very complicated, and there's a lot of in situ testing, modeling, trying to understand it, and still poorly understood. Okay. In fact, one of the most difficult things to model is if you take a piece of wood, you throw it in the fire, you actually have all 5 of the processes going on at the same time. You can end up with the middle of the material in drying, some annular area in pyrolysis. You can have oxygen coming in from the outside doing some amount of combustion that is reducing on the charcoal going out and then burning H2 on the outside. The oxygen can be burning the charcoal. You can be generating oxygen on the inside from the pyrolysis that's coming out combusting and then reducing on outer layers. It can be going back and forth too. So you have this heterogeneous multi-directional series of processes going on. And in a piece of wood that's burning in the fire, you'll usually, in the beginning, have all 4 of those things going on at the same time. And to the degree that you have any void spaces and you have tar, you can get some amount of cracking in there. So now we have 5 processes going on at all the time. Okay. What?
I know why fire is so fascinating.
Yeah. It makes well. This is why folks like us without big university grants can do something in it, because it is so difficult to model. Our modeling is such a nonlinear, multivariable problem that we're just getting to the point that we can learn interesting things through modeling with it. But so much of combustioneering we got 90% of the way to the good stuff through C of the pants engineering. You know, you play with it. That's why we do so much with motors. Now, to do that, those last stage things, there's a lot that can be done through modeling and more contemporary technology. But gasification is so untouched right now that, like, I'm happy to work with 90%. Okay. Okay. So again, the problem with explanation through ring 3 is it's wrong, or again, it's incomplete. And what you start learning the further you go into this thing is you don't have these things called drying, pyrolysis, combustion, reduction, and cracking, but you have these kind of variable processes that that you can control in very significant ways to what they produce and introduce to steps later in the process. And by well controlling those, you can significantly solve things that are usually real issues in a gasifier, like tar problems, okay, or gas energy density. And while solving those problems, you know, when we start like this, we're looking at this as a thermochemical problem. But you see very clearly, once you actually start building these things and running them, that the ag problems in it are actually harder and more important to its long running than the thermochemical problems. The ag problems being the material handling things. The hardest thing to deal with in a solid fuel, I've found, is making it flow, is making it move. You see very quickly why we went to gases and liquids. It wasn't a massive conspiracy. It's just easier. It's so much easier to pump and valve and mix. And solid fuels are a disaster. So as you're solving all these thermochemical problems, you're also solving this very difficult mechanical problem in the presence of gravity, which gives you some constraints on what you can do. So I like to say a gasifier design is a 3D thermochemical, mechanical, gravimetric puzzle with no discrete puzzle pieces to draw the picture. Okay? That's why it's a humanities problem in the end. So, to help in that, I have a couple of we're almost done. You guys take another 15 minutes if you're falling over. Staying with me, kind of? Back on slide 3? Okay. So, a couple of heuristics to help understand what we want to do in a gasifier over these variable processes. Actually, I'm going to deal not with the variable things first. We saw in the updraft and downdraft gasifiers, they dealt with the thermal relationships and the chemical relationships differently. Unfortunately, how you want the thermal relationships to get established in the gasifier are completely unrelated to the chemical relationships, which is what starts this puzzle. The thermal relationships, the ideal gasifier thermally is set up in the progressive thermal relationships. It would really be a sphere. Well, a sphere within a sphere within a sphere within a sphere. The center sphere would be combustion. All of the heat coming out of that would be taken up into reduction. All of the heat from that would be taken up in pyrolysis, all the heat into drying. So all of your energy created in the middle would get captured in your progressive processes. That would be thermally the most efficient gasifier. Unfortunately, a spherical gasifier is not a terribly useful thing to build, operate, or deal with the chemical relationships. But you can see that essentially is an updraft gasifier. You can make some of these thermal relationships better by doing cylinders within cylinders. You can still lose things out the top or bottom, not to the next process step, but to atmosphere. But this is why you often see gasifiers done as a series of cylinders within cylinders. Or at least that's how we do it. We try to do it hot to cold going out, not solve it through insulation, only using insulation when you have to, but first set up the processes such that any waste is your input to your next process. And that makes them more simple. Okay? So, ideal thermal relationships, easy. Ideal chemical relationships, mess. Looks nothing like the previous picture.